Can you see my screen now? Can somebody respond?
We can see. Yeah.
Okay. So yes, I'll be doing the transactions and concurrency control lecture for all. But for now, for the time being, I'll be going with part 1. So if we have time, we'll see about part 2, since it's a very long lesson and lot of theories. And we informed in the group to check the lecture slides, or at least the lecture and come. So I hope that you guys would have checked them. So yeah, let's start now. Transaction and concurrency control. So in the part 1, what we will be covering is the definition for the transaction, some properties that are there in the transaction, also about concurrent executions and what have the conflicts that occur due to concurrent execution, and about some protocols and about aborting a transaction. So before going with the meaning of transaction, we have to understand one thing. Now in PF and all, we have done so many applications, we have done so many softwares. So we know in an application we have several functions. We have so many functions that we code in the application. But to operate these functions, we need the data that is stored in the database. All our data is there in the database. But the database is just a storage unit. It's just a storage unit. So this retrieving data or whatever we write to the database, it is not done by the database. It's just a storage unit. But to perform these functions, definitely we need to read some data from the database, or sometimes we even have to write data to the database. So for this, we will be using the DBMS. So DBMS means Database Management System. So our application must be connected to the DBMS so that we can read data from the database or write data to the database. So now as a user, we see our program or this application or the program as operations. We are carrying out so many operations. But what the DBMS sees is, it only knows that it is going to read some data from the database or it is going to write data to the database. So DBMS is only concerned about read writes. Now for example, if we take update. So to do the update operation, first of all, we must read data from this database and then do all the modification and write that data back to the database. So that is what DBMS knows. It's just reading, writing, reading, writing. It knows it as a sequence of reads and writes. So we are seeing it as the user program as operations, but the DBMS is seeing it as a read write. So that is what we call as a transaction. So transaction means the DBMS's view of the user program. How the DBMS is seeing the user program. And they have called it as an abstract view. So abstract means that it is not actually happening, or it's not the weave that the DBMS sees is not the actual weave. It is just an idea that the DBMS has. It's something like virtual or logical. So transaction means the DBMS weave of the user program, and that weave is abstract. So that's the first point. Now this is in technical terms, this is the definition, but in simple terms if we have to tell, transaction is a sequence of read and write that belongs to a single unit of work. So the first point, the two main points are there here, sequence of read and write and a single unit of work. It's very important, this term is very important, single unit of work. So let's see what these two terms mean. Now one example of transaction that we also do in our day-to-day life is money transfer. So now I have taken an example. I have two accounts, account A and account B. I am going to transfer money from account A to account B. So what should happen? From account A, I should get the balance and subtract that amount. So if I am transferring 100, I should subtract 100 from the balance from account A. The same amount I should add to the account B. From its balance, I should add 100 to the balance. So we know it's an update statement. So that this transferring, from account A, we have one update statement. In account B, we have another update statement. So there are two update statements. So there are two SQL statements here. Now I have a question. So two SQL statements means how many transactions are running here? Like if anybody knows, they can put it in the chat. Anybody has an idea? Okay, so let's see. We have two SQL statements here, but this does not mean there are two transactions. No, there are no two transactions. So that's the point. What is that is, now we are transferring a balance. Okay, so that is our work. What is our work? I am going to transfer balance from account A to account B. So that is my unit of work. So for this unit of work, there is one transaction. So inside that transaction, I have two update statements. So that's the theory. That is what it's meant by a single unit of work. You are doing this transaction for this transferring work. This is your work. You want to transfer a balance. For that you are doing this transaction. So in this case we have two SQL statements. Similarly, we can have one SQL statement, we can have multiple SQL statements, but for one unit of work, you have one transaction. So here the unit of work is, we are transferring the balance. Okay, so that is meant by a single unit of work. The next thing is this sequence of reads and write. So what is this sequence of reads and write is, now to do this update, the DBMS has to first read the balance in account A, and then it has to modify the balance, that is write. Similarly, to do this update, the DBMS has to read the balance in account B and then update that also. So we see it's a read-write sequence. So the DBMS is working as a sequence of reads and writes. So that is what is meant by this sequence of reads and write. So transaction, it is a sequence of read and write, and it belongs to a single unit of work. So inside one transaction we can have one SQL statement, two or even many SQL statements. So this is what we mean by transaction. So did you all understand this, or do you all have any doubts here, or should I explain? If so, please put it in the chat. Anyone needs an explanation again? Okay, seems like no, so I'll move forward. The next topic is properties of transaction. So this is very important because there are questions asking to list the properties of transaction. Some are there to explain the properties of transaction. So since we will get structured question, most probably this can be a question. So pay attention to this. So the properties of a transaction, it is, in simple terms, we define it as acid property. So remember acid so that you can remember all four properties easily. So A is for atomicity, C is for consistency, I is for isolation, and D is for durability. So these are the 4 properties. So if they say list the properties of a transaction, just write all these 4 properties: atomicity, consistency, isolation, durability. If they ask to explain, then you have to give a definition for each of them. So let's see what these 4 properties mean. Let's start with atomicity. So atomicity means, in our simple terms, all actions happen or nothing must happen. You have to either perform all the actions for a transaction or do not perform any action. So that's what it means. Now let's take an example. I'm transferring an amount of 100 from account A to account B. So from account A, as I said before, I should subtract 100. From account B, I should add 100. So now when this transaction starts, think it started with A, it subtracted, okay, then it went to account B, it added, and it's fine, it's complete. It did all the actions are complete here. The 2 update statements are complete. In that case, it will commit the transaction. So all the actions are completed. So we are going to commit the transactions. So in such case, what happens is all the actions are executed. Whatever SQL statement is there, it is executed. Every actions will be executed by the DBMS. Now let's think why it transferred from account A. So that means it subtracted 100 from account A. But before it could add to account B, something happened. Some crash or something happened. So what happens is this should abort the transaction. It cannot complete, so it has to abort the transaction. So abort means it should undo whatever it did so far. So now if it has already subtracted rupees 100 from account A, it should undo this. So the account A's balance must be equal to the initial balance now. So it should undo that. So once undone, we can see none of the actions are executed. So those are the 2 things it does to maintain this property. Either do all the actions or do nothing. So that is meant by atomicity. So to this is from the lecture slide. So this property says that the transaction is executed as a single unit of work. So that I explained. And what? For every transactions, either all action within the transactions are carried out or none are. So that is the meaning of atomicity. So if you want to explain atomicity, please explain this, write this entire statement. So a transaction might commit after completing all of its action. So if all the actions are complete, it might commit. Or it could abort after executing some actions. So some actions means, as I said, it did this part, it did, but it didn't do this part. It has done it partially. So it can abort after doing some actions also. So in that case, it should undo whatever it did. So for that, we will use a DBMS log. So DBMS log will store all the transaction details so that we can undo easily. We can go backwards easily. Then atomicity of the transactions. To maintain this atomicity, we can do it in 2 levels. First is the database level, the next is from the front end. So in the database level, we can use functions and we can use stored procedures. So I think you all know what is functions and what is stored procedure. We studied that in the 2nd year. So using this, we can make sure we maintain this property. That is, we will start the transaction with the keyword begin transaction. And then we can write our SQL statement. Here we can write multiple SQL statements. All what are the actions you want to perform, you will write it. And once those all are written, at last you will commit the transaction. So what will happen? It will begin the transaction, it will perform all the actions. So only when it completes, it will commit. So in between, if it crashes also, it wouldn't have committed because the commit is at the end. So that is the way to ensure atomicity through database level. Then from the front end, that is from the application that we use, we can use connection objects. Now I think you all remember when we did in PAF or all other projects, we will use an object like this, connection con. For example, we will use connection con. And on this object only we will define so many properties. And then even executing, like using prepared statements and all, we will do on this object. So we can use a connection object, and then we can set this property auto commit as false. So at the beginning, when we start, we should set auto commit as false. Then you can perform all what you want to do. And now if you want to commit, if this is your committing point, make sure to set the committing point. So at the beginning, make it false, auto commit is false. And then when you finish all the actions, you can set the committing point at last when you finish all the actions. So that is the way to ensure the atomicity from the front end. So that is all about atomicity. Then next we will go for consistency. So consistency means we have to maintain correct data. So at the end, whatever you do, read, write, any operations that you do, at the end, whatever we give to this database has to be correct. So maintain correct data set. So that is meant by consistency. So in other terms, as a user, if we give the correct details to our application, the output that we get also must be correct. So that is what that means. You give the correct details, so output must be correct. Now for example, I'm going to transfer an amount from account A to B. The same example, but the balance in account A is 50. Now the current balance in account A is 50 and I'm transferring rupees 100 from account A to B. So now the balance becomes minus 50. So this cannot happen. At any cost, this cannot happen. Balance has to be either 0 or more than that. It cannot be minus 50. So to ensure that this doesn't happen, as the programmer, we must write the correct logic in the program. When we are coding for the application, we must write it correctly. So that is only maintaining consistency. We make sure the data is correct. So that is the consistency in simple terms. So in the slide it tells database consistency is the property that every transaction sees a consistent database instance. So consistent database instance means, now let's take an example of two transactions, T1 and T2. Can you hear me?
We can hear you, but
I think I got disconnected.
It's okay.
As far, like, can you tell which point it got disconnected?
You started drawing the table.
The consistency, right?
Yes.
Okay. Thank you. So now in consistency, this consistent database instance. So we have two transactions, T1 and T2. We think T1 row it modifies A and T2 is going to read A. So that is what it's going to do. Now if T1 does some mistake, we think it made a mistake now in writing A or in modifying A, but this T2 is going to read that A only, and then next if it's going to modify A, it will take the incorrect A value and then do some modification to that incorrect value. So that cannot happen. So if this is correct, whatever is dependent on this transaction will also be correct. So that is what it means by consistent database instance. So to maintain consistency, the main person responsible is the user. So whoever is writing the program logic must write it correctly so that we can guarantee consistency. And there is another special thing we can use to maintain this consistency is our integrity constraints. So we have studied about integrity constraints in the previous years. To remind you all, it can one example is key constraint. Our primary key cannot be null. So likewise, we can apply some integrity constraints as well. Referential integrity constraint or assertions like that, we can apply these constraints as well. And things like what I did for this account, you have to code it in the program correctly. So by that, we can maintain the consistency of the transaction. This example given in the slide is transferring the balance from one account to another. The total amount in both accounts before and after the transaction must be equal. So what this means is, if we are transferring rupees 50 from account A to account B, I will subtract 50 from account A. That same amount only I must add. I must add rupees 50 in account B. I can't subtract 50 from here and add 100 here. So that is what this example means. So both amounts must be same. So that's about consistency. The next property is isolation. Isolation. So before telling what is isolation, now this is a small example. Now we'll consider you have an account. So at the same time, you are using your laptop to view the balance in your account and also your mobile to view the balance. So both should tell, now if your balance is 700, it should give the balance as 700. This can't give 700 and this can't give 500. Both should give the same balance. So that is what you call as isolation. In terms of transaction, think from laptop I am transferring and withdrawing rupees 700 from my account, and from my mobile I am withdrawing rupees 300. So what the DBMS must do is, it should understand that this transaction and this transaction both are two different transactions. This is independent of this. Both are not the same. Although both the transactions are done on the same account, it is a separate transaction and this is a separate transaction. It should know that these two are independent. So that means these two are isolated from one another. So for that, the developer must set an isolation level. So that's what is meant by isolation. So now this is just for one account. Now if we consider our normal transactions, we know within a minute or within a second we can have multiple transactions and they can run parallelly also. So the DBMS must be able to identify all these transactions independently. Without identifying this as a part of this or this as a part of this, it should consider this as a separate one, this as a separate one. So that is what we call by isolation. So this is from the slide. Isolation property ensures that even though actions of several transactions are interleaved. So interleaved means parallel. Here I said multiple transactions running parallelly. So if the actions of several transactions are interleaved, if they are parallel, the net effect is identical to executing all transactions in some serial order. So what this statement means is, now I said I am going to withdraw 700 from here. I am going to withdraw 300 from here. But these two are happening parallelly. Let's consider these two happening serially. So serially means first one, this has to finish, then this has to finish. So first it will deduct 700, then it will deduct 300. So totally it has to deduct 1000 from your account. So this is the output we will get if it is done serially. So although these transactions are interlinked, so that means although these two are happening parallelly, the final outcome must be from this account 1000 rupees should have been deducted. Whatever order you do, 1000 rupees should have been deducted. So that is what this tells. The net effect is identical to executing all transactions in some serial order. So that is the meaning of isolation. And the last property is durability. So durability means this ensures that transactions survive system crashes and failure. Now let's take an example that you go to the bank, you want to deposit an amount. So instead of doing it through the machine, you are giving the person who is there in the bank to do this. So now that person will enter all the details to the system, and then he will tell it's done, okay, you will come. But before those details get entered to your database or before the details get updated, think there was a system crash. The system crashed. So the next time when you come, your amount will not be there. The deposited amount will not be there. But practically that cannot happen. So what this durability means is, even if there is a system crash, what has to happen is all your transactions must be rolled back. That means it must be aborted, but still those details of the transaction must be there stored somewhere so that you can recover the system and then do the transaction back again. So now if your transaction commits before your crash, it's fine. The things will be reflected in the database. But it's not yet committed. You didn't commit it yet. There was a problem. So it will roll back the transaction. So what it will do, again it will maintain a log, and what happened? Once it recovers all the things back again, you can do this transaction once again. So the details are still there, so it will commit all the transaction back. So that is important to maintain. So therefore recovery manager is very important to maintain this durable property. So you will learn more about this in the crash recovery lesson. So that is meant by durability. Although your system crashed, the transaction details must be available somewhere. It should not be lost. So that's the meaning of durability. So these are the four features, four properties of transaction. Do you all have any questions in this section, or do you all want me to explain any part particularly again? Okay, I think it's a no, so I'll move forward. So next is about transactions and schedules. Sorry, somebody asked the isolation part. Okay, I'll explain again. Now isolation means, you think you have an account. For example, your account is there in a bank. So what you are going to do is, from your laptop, you are going to do a transaction. That is, you are going to withdraw 700 rupees from your account and transfer it to another account. So that you are doing it from your laptop. At the same time, you are using your mobile to transfer another 300 to some other account. So you are doing two transactions. You are transferring 700 using your laptop, and you are transferring another 300 using your mobile. But both these actions you are doing it on your account only, but using two different devices. So now if the DBMS thinks, okay, these actions are happening on the same account, so both these transactions are same, it might sometimes reduce 500, or it might sometimes reduce 400 from your account. It won't reduce the correct amount. But you know that this is a separate transaction, this is a separate transaction that you are doing. So definitely the DBMS must understand that this and this both are two different transactions, two independent transactions. This transaction is not depending on this, or this transaction is not depending on the transaction done using the laptop. So that means you are going to isolate the transaction you did using the laptop from the transaction you did using the mobile. So for that we should set an isolation level. So that has to be done by the developer. So simply isolation means when you have a transaction, when you have a system, there will be multiple transactions that is running parallelly on that system. So the database must understand that each of these transactions are independent of one another. It should know to isolate each one of them. So that is what is meant by isolation. So as I said, the first point tells that. The second point what it tells is the net effect is identical to executing all transactions in some order. So now from the laptop if you withdraw 700 and from the mobile if you withdraw 300, think you are doing first without doing it parallelly, you are first withdrawing 700 from your laptop. Then you are withdrawing 300 from your mobile. So what is the final outcome? You should have deducted 1000 from your account. But here it's happening parallelly. So when you do parallelly also, it should make sure that it has deducted 1000 from your account, although two transactions occur parallelly. So that is what this statement means. So did you understand that part? Are you okay with it? Okay, so next is about transactions and schedules. So as I said, DBMS it sees transaction as a series of ordered actions. So ordered action means your reads and writes. So actions includes reads and writes. So means it's a sequence of read and write. So DBMS is seeing a transaction as that. Now there will be multiple transactions and these transactions are occurring parallelly also. So the DBMS must maintain a schedule, which transaction to run first, which transaction to run next. Likewise, it should maintain a schedule. So that is the use of schedule. So in this example, if I take, I have two transactions T1 and T2. So I can do it from top to bottom. I can start with this, come to T2, again come back to T1 and do this from top to bottom. I can even go this way. So that timeline we have to schedule it correctly. But when scheduling, remember it has four main actions. It performs four actions. So the first is read and write. So first one is read, second one is write. So the example notation is, if transaction T is reading object O, so that means we have to write a subscript T and an O, object O. But we do not have to write this subscript T, we can just write it as RO. This is also correct. So if the transaction T is writing on object O, we can write it as WO. So these are the first two actions. And the next two actions is commit or abort. So if your transaction is complete, you will commit it. We can just write commit, we don't need this T. If you are going to abort, we can write abort, no need this T. So the four actions are read is the first action, write, then commit and abort. So those are the four actions of a schedule. So remember that point also. Now before going to the next part, we'll check on this. Now we said the system is doing the transaction parallelly, and we know to process a transaction we need our CPU. So CPU is our processor, but CPU it can only execute one instruction at a time. So how are we going to do it parallelly? We say it's happening parallelly, but CPU can only process one data at a time or one instruction at a time. So how are we doing this parallelly? So what this means is, first now let's take this transaction. So T1, first it is reading object A. So what it will do is, it will read from the disk to the memory. T1 is going to read object A from disk to the memory, and then it's going to modify. So we'll think that T1 is doing that doing a process here in the CPU. So it's going to do some modification. So it's processing that. Now T2 came. T2 is going to start. So it has to read B. So what did I do? T2 is also reading B from disk to memory. T2, it has read now. So T2 is also in the memory. T1 is also in the memory. Just that T1 is processing its instructions while T2 is still waiting in the memory for the CPU. Until this finishes, it will wait. So that means we can see T1 is also active, T2 is also active. Both are in the memory, both are running. So that is what is meant by parallel. So both are in the memory, both are running, but the thing is only one transaction can process at a time, but both are still active. So that is what this means by parallel. So that's one point. So why I said that was, now we said the transactions are done parallelly. So why we are doing it parallelly, this is one of the reason. So this entire thing is also there in the questions. They can ask the sentences as it is. So we'll see. So DBMS interleaves the actions of different transactions to improve performance. So what it means is that the DBMS is doing parallel transactions. Why? To improve the performance. By doing each of these transactions parallelly, you can improve the performance. So the motivation for this concurrent transaction is that CPU can process one transaction while another is waiting for a page to be read from the disk. So what? CPU can process one transaction while we can read another transaction from disk to the page. Page means this memory. To read, we can do that. So while processing, we can do this also. So that is one motivation of the concurrent transaction. And the other thing is, we are going to interleave short transactions with long transactions. So that means we can have multiple transactions. So if you have a short transaction and a longer transaction, if we run these two parallelly, we can complete the transaction more quicker. It will be more fast. So that is also another motivation for concurrent transaction. So those are the two motivations for concurrent transaction. So did you all understand this point, or should I explain this thing once again? Can somebody respond if you all need? Okay, so let's move to the next one. Now a simple thing, we are telling we have to perform the transactions concurrently. So if we are doing it concurrently, we have to schedule it. So somebody might think, why we need to do it concurrently? We can do it serially, so we do not need any scheduling or anything, right? So the question that arises here is it important to do things concurrently? Why doing these things concurrently is important? So we'll see this. Now I'm taking two transactions, T1 and T2. So what T1 is doing is, it's calculating interest and it takes 2 hours. Okay, so it's calculating interest and it takes 2 hours. And T2 what? As a customer, they are going to withdraw fund. So that is T2, second transaction. And these two, we will think this is happening serially. First of all, without a concurrent or parallel, it's going to happen serially. So think, you came to withdraw the amount, but before that the manager started calculating the interest. So if this is happening serially, what happens is, you have to wait for these 2 hours until this transaction completes. You can't withdraw and leave. You have to wait for this to finish if we are doing it serially. But that is not practical at all. So that is why we need to do things concurrently. But doing concurrently, there can be conflicts. Now, for example, here, think these two. So I said it has to happen parallelly, no? So the manager started calculating the interest within that time I came to withdraw an amount. I withdrew 100 and I went back. What happened? This action is not yet over. So for the amount I withdrew, there won't be any interest added. So without the interest only, you would have withdrawn the amount. So that is a conflict again. So there are conflicts like that when we do things parallelly, but that we will discuss after some time. So that is so through this you must understand that doing things concurrently is important. So now I am going to go for the scheduling transaction types. Before that, do you all have any doubt? The last part which I did, from this if you all have any doubts, please tell me. Okay, so yeah, let's move. This scheduling transactions, we have three types of schedules. So one is serial schedule. This other one is equivalent, and the third one is serializable. So we have three schedules: serial, equivalent, and serializable. So we will see what each of them mean, and this is also very important because there are questions, structured question to describe what is the what serial schedules means or what serializable means. So definitely we can get that in our exam also. So let's see what is serial schedule. So serial means that does not interleave the actions. So does not interleave means there is no parallel execution. So if we take two transactions T1 and T2, T1 will start means until it finishes T2 will wait, and then T2 will start, and then only it will complete its action. So only after one transaction is over, another transaction will start. So does not interleave. So that is serial schedule. So when we do it serially, definitely there are no conflicts, because when we do parallel only we find some conflicts. Since it's done serially, this is over, then only this is going to start. So there are no conflicts between these two. And the very important point is database ends with the correct data. Always the database is going to end with the correct data. So remember, this is called as the effect of serial schedule. Remember, this is the effect of serial schedule, because this is needed after this. This is the effect of serial schedule. So the effect is database will always end with the correct data if we run a serial schedule. So that's about serial scheduling. The next one is equivalent scheduling. Now I'll take two transactions again, T1 and T2. So what I do is I will start with T1. These are running parallelly. Then I'll do T2. Then I'll complete T1. So T2 is complete here. It's over. Okay. Now this is schedule 1. This is my first schedule. I have another schedule. The same two transactions. Okay, this is S2, my second schedule. I'll start with T1, I'll then go for T2, I'll complete T1, then I'll complete T2. So this one I did it in a different way. Okay, but we'll think after the end of this schedule, I had a value called A. At the end it gives value as 1000. Now this schedule 2, this is also going to give the value of A as 1000. Let's assume like that. Okay, the ways of executing these two were different, but this also gave 1000, this schedule also gave 1000. So that means the outcomes are equal. From both these schedules, the outcome is equal. That is what we call as equivalent schedules. So for any database state, the effect of executing the first schedule is identical to the effect of executing the second schedule. So the effect of first schedule is identical to the effect of the second schedule. So such schedules we call as equivalent schedules. Then the third one is serializable schedule. So serializable means, before going to that, now serializable, the main thing is now we are trying to run our transactions parallelly. So now if I take two transactions T1 and T2, if I run these two parallelly, I am going to get an output. So likewise we'll think A is 1000. I got the A output as 1000 when I run this parallelly. The same thing if I do it serially. I am going to try doing these two serially. So first I'll run T1 and then T2. So first I have to run this, then I have to run this. Okay, T1 is over, then I am running T2. And think I received the output of A. Assume that I received the output of A as 1000 here also. Now this is a serial execution. The same thing if I do it this way. T2 first, T1 next. So I have to run this part first and then I am going to run T1. So if this also gave me 1000 as the output for A. So we see this is a parallel schedule. These are parallelly happening transactions. The output that it gave is equal to the output of the serial transaction. So serial transaction always ends with the correct data. As I said, it's going to end with the correct data. So that means this data it ended is this 1000 is correct. So when you run transactions parallelly, and if the output gives the effect of serial schedule. So the effect of serial schedule means it's going to give the correct data. But the difference is it's running parallelly. So that we call as serializability. That means you can run transactions parallelly, first point, and the effect must be equal to that of serial transaction. So that is called as serializable schedules. So you have to run parallelly and the effect must be equal to the execution of serial transaction. So that is meant by serializable schedule. So do you all have any doubt up to here? Can somebody respond like you all have any doubts up to here? Is this clear? Whatever I did up to here. Okay. So this is the serializable schedule and that's what we call as serializability also. So serializability means multiple transactions are executed concurrently, first point, parallelly, and must be equivalent to some serial execution of transaction. So serial execution of transaction means the output has to be correct. So in this case, if you have a serializable schedule, it is going to preserve consistency property. So this point is very important. This is there in the MCQs as well. So serializable schedule will preserve the consistency properties. So but although you are running concurrently, this order doesn't matter. You can run it in any order, but at last the output you get has to be the correct output. So when you run multiple transactions parallelly, if the effect of that transaction is equal to that of a serial schedule, so we call it as serializable schedule. So that's all up to the scheduling part. So next we have some anomalies that we have to discuss. So anomalies, as I said, the conflicts that we get, some problems that come because we are running transactions parallelly. So now this is the first example I am taking. Think I have a value called A. A is 15. My value of A is 15. So it is reading A from here. The transaction T1 is going to read A. It will read A as 15. Now transaction B is also going to read A. It will also read A as 15. So both of them, they read A as 15. No problem. And we know it's correct. A is 15. Okay, fine. There is no problem. Now consider this instance. Think this transaction T1 changed A to 20. It modified A to 20. Now transaction T2 comes. It is going to read A. Now here is the problem. What to read? Whether to read 20 or whether to read 15. Is this correct or wrong? We don't know. So that is where anomalies start. So you have to understand, when there are two reads one after the other, when there is read, there are no issues, no problems are coming. But even if you have one right here, there is a problem. So these anomalies mainly arise when we have at least one right. So it can be right read, or it can be read right, it can even be right. So at least if you have one right, okay, you can end up with anomalies. So that's the first point. So there are three types of anomalies. One is your right read, other one is read right, and other one is right. So there are separate names for this. And we have to remember all these three anomalies also, because sometimes they can ask to explain. There were questions in the past paper as well. So let's first see right read conflict. So the WR conflict. So WR means, the other names we can give is dirty reads and reading uncommitted data. So remember all these three names: reading uncommitted data, WR conflicts, dirty reads, all are same. So that's the first anomaly that we are going to check. So now let's take this example. I have two transactions, T1 and T2. So what T1 is doing is, it's going to transfer fund from A to B. So it's going to transfer rupees 100. Then I have a T2. It is going to calculate 10% of interest. So those are the two transactions and what they are going to do. And this is happening parallelly. So now I will take this transaction. I'll start. We are starting with T1, read A. So read A means A is what? First 1000. Okay, A is 1000 here. Modify A. So I have to transfer from A to B. So I have to subtract 100 from account A. So that means it will end up with 900. Then we are coming to transaction T2. So T2, it's going to read A. So what is A now? A is now 900. So T2 is reading A as 900. Now it is going to write A. So what is this write? Calculate 10% interest on A. So 10% of 900 is 90. So that means the modified value of A is 990. 900 plus the 10% 90. So 990. Now it is reading B. So what is B? B is 2000. So I took 2000. Okay, it took 2000. It read it as 2000. Now it's going to modify B. So 10% of 2000 is 200. So 2200 is the value of B now. And be very careful here. It is committed. It modified and now it's committing the transaction. And then again T1 starts. T1 is reading B. So now what's the value of B? 2200. So 2200 is the value of B. It's going to modify. So modify means I transfer from A to B. So if I deduct 100 from A, I should add 100 to B. So that now final value of B is 2300 and I have committed here. So now what happened to A? Our final value of A is 990. Final value of B is 2300. Okay, so that is what happened from this execution. Now let's see, I'm going to do this in a serial order. So that means I'm going to do T1 first, T2 second, and next T2 first and T1 second. So let's see. I have T1, I have T2. So first I should do T1. So T1, what's the first action? Read A. So A is 1000. Okay, so 1000 I read A. Then modify A. So I have to deduct 100, so I deduct 100, so that means 900. So now this is serial, so I'm not coming to this, I have to finish this first and then only come to this part. Okay, so then only I have to come to this part after finishing T1. So next is read B. So B is 2000. So okay, value is 2000. Modify B. So what's the value of B now? 2100. And then I commit it. Now I start with T2. So T2, read A. So now A is 900. So I read 900. Modify A. So that means I am going to add 10% interest. So 10% of this 900 is 90. So that means A's value is 990. Now read B, the next one. So I read B, B is 2100 and I have to modify B. So that is 10% interest I should add. So 10% of 2100 is 210. So 2100 plus 210 is 2310. So the B value is 2310. So what this gave, this transaction gave A as 990. Sorry, this schedule gave as 990 and B as 2310. So let's compare. When we run it parallelly, A's value is 990. Okay, when we run serially like this, also it's 990. But B is 2300 and here it is 2310. So now in this case, it is not equal. The outcome of this parallel execution is not equal to that of serial. That means we know it is somewhere it's not the correct data. So now I'll do the other way. I'll try doing T2 first and then I'll check T1 and see. So T2, first I have to read A. So read A is 1000. So modify, so 1000 means again it's 100. So 10% of 1000 is 100. So I add 100, so 1100. Now read B. So B is 2000. So 10% is 200, so it's 2200. I commit it. Now I start the other one, first transaction T1. So value of A is now 1100. So read 1100. So I have to calculate. I have to reduce 100. So I'm doing this second. So I should reduce 100 from A. So that means this is 1000 now. Then I have to read B. As it's mentioned here, read B. So B is 2200. I had next one, modify B. So I have to add 100 to B, 2300. So this is giving A as how much? A is 1000. And B is 2300. So we can see although B value is equal, A is not equal. Here although A values are equal, B is not equal. So we see this transaction that we did parallelly does not give the output that is equals to any serial one. At least it's not equal to one of the serial execution. So that means this is wrong. It has ended up with incorrect data. So that is the first anomaly. So that is due to write read anomaly. So I'll show where we have the anomaly. We'll see it is write read. So we can start read A, write A, read A. So we did WA-RA. So there is WR here. This is the place where we are getting the conflict first. Now I'm going modify A. Then read B, modify B, I committed and I read R. Again there is a WR here. But this is not a conflict. Why I am telling this is not a conflict is because this committed the transaction already. So here since the transaction is committed, this is not the conflict. So our conflict point is this. This is where the anomaly arises. So that is reading uncommitted data or WR conflicts. So is this clear or you all want me to explain again before I move to the next anomaly? Can anybody respond, because this is a hard part? Okay, thank you. So that's about write and read conflicts. Next is unrepeatable reads, that is read write conflict. So remember both the names, unrepeatable read and read write conflicts. So let's see how this is happening. Now I have two transactions, T1 and T2. So I have two transactions, T1 and T2. So T1 is going to read A, then T2 starts read A, then modify A, then it's going to commit. So I'm committing that. Next T1 starts back again, read A, then again modify A, and then commit. Okay, so what T1 is doing is it's incrementing A by 1, T2 is decrementing A by 1. So this is going to increment, this is going to decrement. Now let's consider A is 20. Our initial value of A is 20. So now this transaction starts, it is reading A. So A is 20. So the next T2 starts, it has to read A, it read A as 20, then it modified A, so it has to decrement A by 1, so A is 19, it committed, and now it is again, T1 is reading A again, when it read this A now it is 19, A has A's value is 19, but if you see T1 properly, you can see it started with a read A. It did nothing, it didn't do any calculation, but again it read A. So when it read A first time it was 20, it didn't do any of the calculation, and when it came here it is 19. So although the T2 changed the A value, this one didn't do any calculation, no modification or anything. When it read for the second time it is 19. So this is what we call as unrepeatable reads. Read write conflicts. So that conflict occurred here. Read write conflicts. So that is the second type of conflict. Why I am telling this as a conflict is the T1 first read A because it didn't do any of the modification. It didn't even calculate, and when it read again it's 19. That 19 came because of T2. That is fine, but still this one did nothing. Without doing nothing, it doesn't know how it became 19. So that's the problem here. So that is unrepeatable reads or read write conflicts. That's the second type of anomaly. Then the third one is overwriting uncommitted data. So that is, we call it as the WW conflicts. So again there are two transactions here as T1 and T2. So first we have to modify A, then modify A back again in T2, then modify B, then commit, then modify B by T1 transaction, and then commit. So T1 is going to overwrite the value as 1000, T2 is going to overwrite the value as 2000. So that's what it is going to do. So now T1 started, it is going to write the value of A, it's going to overwrite it as 1000. Okay, it changed it to 1000. Now T2 is starting, it is again WA, so it's going to make the value of A as 2000. Now it's going to modify B, B is also 2000, it commits, now it again overwrites B, so B is back, B is now 1000 back again. So at the end we have got A is what? 1000 and B is also 1000 from this parallel execution. Now, sorry, A is 2000. I'm sorry, A is 2000 here, B is 1000. So T1 first it modified A, so A's value is 1000. B2, so T2 modified A back again, so it's 2000. Then T2 modified the value of B, so B is 2000. It committed. Now T1 modified B again, so B is 1000. So the value of A is 2000 and the value of B is 1000. Now this is when it happens parallelly. If I do the same thing serially, let's see, I have T1 here and I have T2 here. I'm going to do it serially. Okay, so first modify A. So modify A means from T1 1000, A is 1000, B is also, then modify B, B is also 1000. Now I am going to come to T2, this commits. Now T2 starts, I am going to modify A. So now A is 2000 and B, I am going to modify B. B is also 2000. So I will commit the data. So at the end from this I am getting A is also 2000, B is also 2000. So that is the output I am getting when I do serially starting with T1. Now if I do the same thing starting with T2, I do T2 first, T1 next. So starting with T2, so modify A. So 2000, modify B. The next one modify B. So B is also 2000 now. I commit, I come to T1. So T1 says modify A. So it is 1000. Then again modify B. So B is 1000 and then I commit. So we see at the end this way is giving both as 1000. So when I did it parallelly, I got A is 2000 and B as 1000. But when I did serially, one serial method gave both as 2000 and one gave both as 1000. So again we see the outputs are not correct. Whatever this transaction did, the output is not correct. So that is another anomaly, overwriting uncommitted data or WW conflicts. So that is this overwriting or WW conflict. So those are the three types of anomalies. Are you all clear with these three anomalies? Do you all have any issues? That's second part. Second part in the sense, this one, unrepeatable reads. I think Vaniga Ratna AI. You want me to, okay. So yes, I'll first delete all the things. So now what unrepeatable read means, it's going to give a conflict from read and write. So I'm going to take this transaction T1 and I have another transaction as T2. So T1 was going to read A. So read A, then T2 is going to read A, then modify A. Read A and it's going to modify A and then it's going to commit. And this one T1 is coming back again and it's reading A again and writing A again or modifying A again and committing it. So this is the order. So now it says T1 is incrementing A by 1 and T2 is decrementing A by 1. So let me consider the value of A as 20. I am assuming A is 20. So when this starts, this is going to read the value of A as 20. Now T2 starts, it is also going to read the value of A as 20 because it's still 20. Now it's going to modify. So what is T2 doing? It's going to decrement. So the value of A is 19. It committed this 19. Now what happens? This T1 is reading this again Now the value of A is 19. So ignore all of these things. Just see only T1. In T1, first it read A. So when it read A, the value is what? 20. Now it is reading A again. The value is 19. Between these two reads, this T1 didn't do anything. It didn't do any calculation. It didn't modify A. It didn't even do a modification. So first when it read, it was 20. Without doing any modification, when it read the second time, it is 19. This modification happened due to T2. But for T1, without doing anything, it has become 19, means there is some mistake there. So that is another anomaly. So did you get that? Okay. So those are the three types of anomalies. So there were questions to write about these anomalies. So remember the normal term as well as the correct word, overwriting uncommitted data. Likewise, remember dirty reads. Those names also remember very well. So now the next thing is unserializability. So what I said, serializability means we are going to run transactions parallelly and the output is equal to that of a serial transaction. But unserializability means that is happening because of these three conflicts. The three conflicts that we discussed right now. The write read or read write or write write. So these three conflicts will make our schedule unserializable. So that means it's going to violate some properties. One of our properties of the transaction will get violated. So what we should do is we must make sure to avoid these conflicts. So in order to avoid these conflicts, we can use a concurrency control protocol. So that is the next part of it. Are you okay with these things, or shall I move to the next one? Okay, so let's move to the next one. So next one is the lock-based concurrency control protocols. So in this lesson, we will discuss only the lock-based. So the main one is strict two-phase locking protocol. We call it in short strict 2PL protocol. And remember, this is also very important because there were questions. There can be many questions from this. So remember these points also very clearly. So when we use a strict 2PL, first there are three rules in this protocol. So simply a protocol means rule only. So there are three rules here. So the first rule is each transactions must obtain a S or a shared lock on an object before reading, and an X, we call it as the exclusive lock on an object before writing. So if I take two transactions as T1 and T2, we have two locks. First lock is S, second lock is X. So S means shared lock and X means exclusive lock. So if this is reading A, we must give S lock. So until if it has the S lock only, it can read the object A. Then if this is writing A, this has to have an X lock. Then only it can modify A. So for a transaction, if it is reading, before reading it must obtain the S or the shared lock, and if it is updating or if it is modifying before doing the writing, it has to have an exclusive or X lock. So that's the first rule. Very first rule is that. Then the second one is all locks held by a transaction are released when the transaction is complete. So now if this is holding S lock and if this is holding X lock, and if this transaction is over, it will release this S lock. So whatever the lock, all the locks that is held by one transaction, it will be released when the transaction is complete only. Unless it completes the transaction, it will not release the lock. So once the transaction is over, only it can release the lock. In between the transaction, it cannot release. Then the third rule is, if a transaction holds an X lock on an object, no other transaction can get a lock SOX on that object. Now I'll take this as another example. Again T1, I have T2. So think T1 is writing A, modifying A. Okay. T2 wants to read A or even write, whatever. Okay. So this is it's going to modify A, so it has gained the X lock. Now T1 has X lock. What has to happen is, since T1 has X lock, for which object we have it? We have it for A. Okay, see the object is A, so we have the X lock. Now T2 wants to read A. So to read A, it has to gain an S lock. But if another transaction has this X lock on the same object, that means object is A. Here also A, here also A. But here if it is read B, then no problem. Here it is telling read A. Since write A has already, the X lock is taken by T1, to read A by T2, it has to take S lock, but that cannot be done. You cannot give the S lock to T2. Because why? T1 already has X lock on A. So if one transaction has an X lock on an object, no other transaction can get a lock. Either it is S lock or X lock, it cannot gain any lock on the same object, on that object. See, the object is same here. So those are the 3 rules of the strict 2PL protocol. And these 3 rules we must remember, because there can be questions. Sometimes we'll have to write the 3 rules, or sometimes it can be there for the MCQs as well. So these 3 rules are very important. Did you all understand, or should I explain again? Can somebody respond, like, should I explain again? Okay. So now we said we are using this protocol to overcome the conflicts. So we have 3 conflicts. What are the 3 conflicts? Write read write, or write write. So we'll see how we are going to overcome these 3 conflicts. So now T1 is going to modify A. It's going to write A. So I have to give X lock to T1. Now T2 is trying to read A. So that means I have to give S lock. But can I give the S lock? No, because I have given X lock to T1 on object A. So when there is an X lock on the object used by one transaction, you cannot give any other lock to another transaction. For the same object, we can't. The third rule, if a transaction holds a X lock on an object, no other transaction can get a lock on that object. So if we apply strict 2PL here, we won't give the this has to wait until this lock is released. So what happened? There won't be any conflict. So this is waiting. So that's the way to overcome modify read conflicts. Now this. First I am going to read A and write A. So read A, I am going to give S lock to T1. Now T2 starts, it needs X lock. Now see, if I give this X lock here, assume that I gave the X lock to T2. What happens to this third rule? It is violated. Why? Because T2 will have X lock on A. T2 has X lock on A. At the same time, T1 is also having S lock on A. So that can't happen. When one transaction holds X lock on an object, another transaction cannot hold any lock on that object. So there is a problem here. So we can't grant this. We cannot give this lock to this T2. We can't give the X lock. So what has to happen? T2 has to wait again until this finishes. So that is how we are going to resolve this read-write conflict. Now the third one is write-write conflict. So this is easy. I have given an X lock. So since it needs to modify, I give X lock. So since X lock is there on A, T2 can't gain any lock. So it has to wait. So this also we can overcome easily. So up to here, do you all have any problems, or should I explain these things again? Okay. And the last part, this is about aborting a transaction. So aborting a transaction, as I said, now we have a transaction. If it is going to abort, if there is some problem, if I have Ti here and if I have Tj here, two transactions, this starts, then this is following, and this is going to be aborted. So if I am aborting this, I should undo whatever the actions I did first. So if I decommitted some actions here, I should undo all those actions here. And also, that is what this first point is. So if a transaction Ti is aborted, all its action has to be undone. Now think, not only that, if Tj reads an object last written by Ti. So we'll take Ti modified A, and Tj, what it did it read that A. So what, it was modified by Ti, it is read by Tj, but what happened? Your Ti is aborted. You are going to abort this Ti. So that means this transaction will undo. So this value of A will be made turned back to the initial value. So here I think A was 20. This modified the value of A to 30. So it is going to read that 30. So it is 30 here. Now this got aborted. So when aborting, it will change this value of A back to 20. So this has read it as 30. So it can't happen. So what must happen? This also we must abort. So if this transaction depends on something that this modified, you have to and that modified transaction, if it is aborted, this also must be aborted. So that is the idea of aborting a transaction. So we can consider two ways as cascading the aborts and unrecoverable schedules. So what cascading means is the one that I explained now. So abort of one transaction causes the abort of another transaction. So if this changed the value of A, this read that A, so I'm going to abort it. So if I'm aborting this, I should abort this as well. So that is meant by cascading abort. Then the second one, and the main reason for this cascading abort is this write-read conflict. We can see that happen here, write-read conflict. So that's the main reason. So that means your transaction which wrote the data abort. So T1, here T1 only wrote your data, it modified the data, that got aborted. So that is WR conflict. So if WR conflict is causing this cascade abort, what we can do? We can apply strict 2PL. So if we apply strict 2PL, we won't have this conflict. So there won't be any cascading aborts. So there won't be any aborts. So easily we can avoid cascading aborts using strict 2PL protocol. So that's the first type of aborting. Then the second one is unrecoverable schedules. So unrecoverable schedules means, now let's consider this. I take the value of A as 20. So it modified A it to 30. So it read that 30 and think this modified that value to 40. And this committed. Now it has committed. Done. Everything is over. It commits. The T2 is over now. T2 has left. Now when it comes back to T1, T1 is asking to abort. So that means I should change this value of A back to 20 and in this T1. I have aborted this T1. But what happened? This T2, it used the 30 that this T1 modified earlier. It did some modification and it committed that data also. So it has committed. So if we have committed, we can't do anything. We can't recover whatever happened here back again. So that is what we mean by unrecoverable schedule. Again, you can see this unrecoverable schedule happened due to WR. Okay, not RW, WR. So that means transaction which read the data commits before the transaction which wrote the data. So this transaction only wrote the data, this didn't commit yet, but this read the data from this transaction and it got committed also. So you can't recover it back again. So to avoid WR conflict, we can use strict 2PL. So if we use strict 2PL, no WR conflict, then no this one also, no unrecoverable schedules also. So simply using strict 2PL, we can avoid unrecoverable schedules as well. So that is the idea of this. So that's the end of part 1. So do you all have any problems up to there? So should I explain anything again? That's all for the part 1. So do you all need any explanations again?
Does anyone have questions? Doesn't look like it.
Yes.
So then let's go to the next part, right?
Okay, as first. So there are some questions, but I don't think the time is enough. Shall I discuss that also? Is it okay? Like 2 questions at least?
Okay. You have time. You have the mini hackathon thing also, right?
Yeah, that's it.
Let's just do 2 questions and let's move to the crash recovery.
Okay. Okay, so here I can't find my things. So let's see this question. Choose the option that are not properties of a transaction. I'm sorry, I'm not getting my pen. Really sorry. Choose the options that are not the properties of a transaction. So I said there are 4 properties of a transaction that was discussed here as acid. So what are the acid properties? Atomicity, consistency, isolation, durability. So the question tells, choose the options that are not the properties of a transaction. Not the properties. Read carefully. So isolation is a property. So it is not the answer. Consistency is a property. So that is also not the answer. Durability is again a property. So that's also not the answer. D says availability, but actually it is atomicity. It's not availability, it's atomicity. So yes, this is one answer. So this is wrong. It is not a property. So D is one answer. And E, partition tolerance is not a property. Again, so that's an answer. So answer is D, E, not A, B, C. They are asking for the incorrect one. So it is D and E. Then let's see this question also. Self-motivation for concurrent, select the motivation for concurrent transaction. So they're asking the motivation. So that points are directly there in the slide as motivations are this. It's given, two separate points were given. Okay, so first one is this. God. So first one, by interleaving actions of transaction, DBMS can improve performance. This statement is true. By interleaving actions of different transactions, DBMS can improve performance. That is why it is using this concurrent transaction. But it is not a motivation. So motivations are these 2 points. This is not the motivation. So don't mark that point. Be very careful. Don't mark that point. The first point, don't mark it. Then CPU can process one transaction while another is waiting for a page to be read from the disk. The second point, that is correct. That is there in the slide as it is. CPU can process one transaction while another is waiting for a page to be read from the disk. So that you can choose as an answer. B is an answer. C, interleaving short transactions with longer transactions allowed to complete quicker? Yes, that is also given in the slide. Interleaving short transaction with longer transaction allows to complete quicker. So yes, B is correct, C is correct. D tells greater system utilization. There was nothing like greater system utilization, so that's wrong. And E says predictable delay from request to completion. Even that is not there in any of the slides, so that is also wrong. So that's one question. And this question tells, consider the given statement about transaction. They are asking for the incorrect statements. For the incorrect, not the correct. Be very careful. So statement A tells serializable schedule preserves consistency. Yes, that point is there in the slide. It's one of the main points. Okay, it is going to preserve consistency. That is mentioned here. It preserves consistency. So yes, that point is correct. So A is correct. So if you have A somewhere, A this answer A, it says A only. So definitely that's not an answer. Answer C tells ABC. So since A is there, not an answer. D tells AC. Since A is there, that's not the answer. So we can omit A, C and D. So we have two answers, B only or C only. So let's see the two statements. B tells, in equivalent schedule, the effect of one transaction on the database is identical to the effect of another transaction. That's true. That is what we discussed here. Only there's a small difference. Here we have it as the schedule. Here it's given as transaction to confuse us. So B is also correct. Now C, in serial schedule, there are interleave actions. In serial schedule, there are interleave actions. But we know in serial, it does not interleave. That's the main point. So that means answer C is wrong. So answer is C only, that is E. So those are the things. And is it okay if I stop now? I'm lacking time and I think we should do crash recovery as well.
Yeah, it's okay. Thank you so much.
Welcome.
Isha, are you there? Shall we start with crash recovery?
Okay, I'll share my screen.
Yeah.
Is my screen visible? Can anybody see my screen?
Yep, it's visible.
Okay. I'm going to do the part crash recovery. So in crash recovery, I will only be going through the main points here. So crash recovery basically means handling failures in an application. So a failure can occur. For example, when doing a transaction at the middle, a failure can occur. So for this, there is a component called recovery manager. We in the database DBMS architecture, here we have a component called recovery manager. The role of that recovery manager is to maintain these crashes, is to recover these crashes. So when a system is running a transaction has 4 properties. I think it has been explained in the previous session. So the main 2 points which the main 2 properties which relates to this crash recovery here is atomicity and durability. Atomicity and durability plays a very important role in crash recovery. So in order for a system to recover crashes, atomicity and durability must be maintained. Like simply atomicity means everything happens or nothing happens. That is, a partial transaction cannot happen partially here. Either the transaction must completely happen or it shouldn't happen. So if you are maintaining durability, it means if a transaction is committed, the effects must be there. So this is the basic idea which must be maintained in order for a crash to recover a crash. So for example, if I take this diagram over here, there are 3 transactions here. The first transaction and second transaction is completed. And the third transaction is an ongoing transaction which has overcome the crash. So, if you are maintaining this atomicity property, the complete transactions must be there even after a recovery occurs. And if we reboot the system, the contents of first transaction and transaction 2 must be there because they are complete transactions and they are already committed. Now the third transaction can't be there. Now if you are maintaining durability, the committed transactions are written to the disk. Now according to this diagram, transaction 1 and transaction 2 are complete transactions, so they must be committed to they are already committed. So if we after a system crash, their contents must be there, but T3 cannot be there because it is an ongoing transaction, it has not been committed. So but this doesn't happen this way in the actual scenarios. That's why recovery manager comes to action in order to maintain crash recovery. So how can we say that all committed transactions are not written to disk? Now if we are telling such a scenario, that is, now suppose a person goes to ATM and wants to do a transaction. Sometimes the server may be blocked because many transactions are occurring at that time, but the server can't, but we can't keep the person for so long to say that the transaction is successful. Then the end user is not satisfied. So that is why what the server, but what happens here is, now when the transaction occurs, the end user is given a message that the transaction is completed. But now suppose if after the person goes away, there is a crash, sudden crash. Now we can't say that the transaction details are not there because this is already we have given the message to the user that the transaction is done successfully. So what happens here is the server doesn't at that same time write the data to the disk. It keeps the data in the main memory, and after the server's load is becoming less, then only it writes data to the disk. So before writing the data to the disk, in the middle, if a crash occurs, it's not practical to say that the data is not available. Now the person has also gone, we don't have the details. So at this time, the crash recovery, recovery manager comes to action here as well. That's why we say that all committed transactions are not written to disk. We are saying this is committed because for the satisfaction of the end user, but this is not actually done. This occurred to handle the workload of the server. And also, partially done transactions are written to disk. How come this happens? Now this happens in scenarios like this. Now suppose we have a data set of 2 gigabytes and the memory has only 1 gigabyte memory area. So now we can't put the whole 2 GB to this main memory because the space is not enough. So what happens is time to time commits occur here. Time to time it's right into the disk because we need to free space for the rest of the memory to put the rest of the data set. So incomplete transaction is committed to the disk in this case. So what if a crash recovery? What if a crash occurs? So the incomplete transactions cannot be written to the disk based on this durability property because only committed transactions can be written to the disk. So these types of scenarios can occur. That's why crash recovery manager comes to action in order to undo these not committed transactions and redo the transactions, redo the committed transactions to be present in the disk. So if you are talking about one of the major concepts is steal. Steal is a very important thing which we must know here in crash recovery. Here what happens is, now if we take a disk, now if we take a disk here, the disk has data blocks and this memory we can have there may be frames. So one data block there is a frame, another data block there is a frame, likewise. So now if this particular disk if a particular data block here wants to write data to this frame, I'm saying it x. Now this already has data. Now see we are already having data, so what I do is I take this x to the disk and overwrite the data here. Now the data which is here can be of an uncommitted transaction, but we are moving it to the disk. So in this case, so in order to bring the new data, we are moving this to the moving this existing data to the disk, but this can be an uncommitted transaction. So system is allowing this. So what if a crash occurs? This uncommitted transaction is also in the disk. This cannot happen. So that also must be recovered. That is what is happening in steal. Now if you are focusing on force means the committed transactions are flushed to disk. Now if you are saying no force, the committed transaction, all the committed transactions are not flushed to disk. Now if you are saying to see about this buffer pool, now it can be force, no steal, force, steal, no force, no steal, no force and steal. So if you are saying force means a commit. If we are committing, it's written to disk. If no force, committing and not written to disk. No steal means ongoing transactions are written to disk, and here no steals mean the commit ones are going to disk. So if this happens, if force and no steal happens, it's auto maintained. Then then if crash occurs, that is not going to be a problem if this is the normal scenario which is happening. But in reality, actual DBMS is running in this way: steal, no force, mode. That is why this recovery manager is important. That is why we need a recovery manager, because ongoing transactions are written to disk. So which shouldn't happen if you are maintaining the atomicity property and durability properties. This shouldn't happen. That's why we are using this recovery manager. Now if you speak, we have a log file. Log file is previously I was saying that a committed transaction doesn't go to the disk. So what happens, that we are giving the message to the end user that is already committed. That is, when we get this transaction, what we do is we log them in a log file. So before giving the message to the user that this is committed, we write the data to the log file. The log file has all the data. So this log file contains every details of every update. It's a text file and it's always increasing, and we have only a minimal amount of information there because we can't have a lot of information there because we are keeping that in the main memory. And if we are having a lot of information and if its size is big, then what we want to do, we can't, it's not possible because it will also take a lot of time if we are writing a lot of data to the log file. That's why we are using only minimal information when we are writing data to the log file. So we are maintaining this log file because in order to identify what we need to redo, what we need to undo, and how are we going to do this, every record is tracked in this log file. So in order for this recovery to occur, details must be properly recorded, must be there in the log file. Then if we are speaking about writing write head logging protocol, that is the valve protocol, the first rule in this is we have to force log record to update before data page gets to disk. Now it's like this. Now suppose we are having suppose in the disk I have number 10. Yeah, I have number. Okay, I'll take it as number 10 here. And in the memory, I'm putting this number 10, and then again there is a change to number 15. So when there is a change, it tracks to this log file. So before this current data block goes to the disk, this log file must go to the disk. We have to ensure that happens. That is to maintain atomicity. If not, by looking at the log file, we can't identify what is in the database. So before this actual data block goes to the data in the actual data block goes to the disk, the log file must go to the disk. And the next rule is all log records written before a commit. That is, log file entries must write to the disk. So when a crash occurs, we have although the crash occurs, we have all details in the log file, so we can recover it from there. So server has the details, so the details we can get back because everything we are writing in the log file. So that is the purpose of having a log file, and we have to ensure that these two rules are properly done in order to maintain atomicity and durability. Otherwise, if these log record, if these log files data is not frequently gone to the disk, and if a crash occurs, we can't recover the data. That's why we always ensure a frequent commit of the log file to the disk. Now, if you are speaking about the val and the log, that is write head logging protocol and the log file has a log record. It's like this. We are having a log record here, and each is having a unique LSN log sequence number. Now we are not having the duplicates here. We have a unique LSN number. Now, for example, if I take this one, now here what has happened is I have the record data as 10, then I have changed it to 25 here, then again 25 to it has been changed to 30. Likewise, when a modification is done, a new record is added. This log file is increasing time to time. The changes are being updated. No, it's not overriding. The new record is being added. Now here, the same in one data page, we have 3 LSN numbers here. So from this, page LSN means the most recent record, which is LSN 25. So this is the most recent record here. So that is we call as page LSN. Now the fields in the log record are as follows. We have the previous LSN here. Then we have the transaction ID. Then we have types. Then we have the page ID, length. Likewise, we are having, I mentioned here the transaction ID. page ID, the starting point offset, length of the record, the old data, new data. Likewise, we are having it here. And the log entry type means, now type can be an update, commit, abort, end. Now end means after all the actions has finished, only we are updating it as end. So after ending means a complete transaction has already written to the disk, and we are not no more needing that particular transaction in the transaction table as well. So here we have another one, compensation log record. That is during undo. When we are undoing means we are going back of the log file, but it doesn't mean the log file is being smaller. We are going backwards of the log file, but we are adding a new record if we are doing an undoing action. So if we are undoing a particular action, we are writing it to the log file. All undone actions are added to the log file. So the log file is growing regularly if we are doing any undone actions. Now if we are undoing that particular action, we can't undo that again. So now suppose while we are doing this undoing operation, a second crash okay, we don't undo that particular transaction again. We don't do that. We can't undone again. So if you are doing any undone, we add the CLR record indicating that we have undo the particular operation. So those are the log entry types. And now if you are linking this log table to the transactions, there are, like, when we are recovering data, we reconstruct this data to two tables. That is the transaction table and the dirty page table. Transaction table has an entry for every active transaction. Now suppose we have already committed the transaction to the disk, then we are not having the record there. Only the active transactions are there. We have one record per each. And in the dirty page table, we have one entry per dirty page in the buffer pool. Here we have a page number and the rec LSN. Now rec LSN means the LSN of log record which first caused the record to be dirty. Now for example, I was saying here about this, we are changing the numbers 10, 20 likewise. So here also I have used the same example. So the same data page is having here 3 transactions have happened. So here page LSN is the most recent one, and rec LSN is not LSN 10, it should be LSN 15. That is the first record which the modification occurs. That is the first one. So that's what we are calling that rec LSN, and the recent one we are calling as page LSN. And moving on to the checkpointing we use in order to minimize the time taken to recover. That is, now suppose we are having data from year 2000 to 2021. So every time in order to recover, we used to read the log table. So checkpointing, it has a LSN number. So the DBMS checks into this time regularly. So this LSN number, we take it from the master record, and we ensure that this is kept in a safe location. Because every time a recovery occurs, they check on this checkpoint. So in order to, if we don't know this particular, if we don't know the LSN number of this checkpoint, we can't do the recovery manager can't do the crash recovery without knowing it. So we ensure that this LSN, this master record, is kept in a safe location. So when recovery is starting in this checkpoint, we consider the begin end check and the end checkpoint. So moving on, I'm now going to say about the Aries algorithm. So saying about the Aries algorithm, the 3 main phases of Aries algorithm is analysis, redo and undo. So algorithm is starting from the most recent checkpoint. So algorithm is starting from the most recent checkpoint. That is recent checkpoint we can find out from the master record, which I said before, master record which is kept in the safe location. And then by reading the log file from the last checkpoint to the crash, that is from here to here, right? It is being analyzed whether there are completed transactions, whether there are partially done transactions. These all are analyzed because we have to make sure that if there are if there are partial transactions, we need to undo them, because partial transactions cannot be there in the disk. Therefore this analysis is done in the analysis phase. So when we say about the redo is starting from the smallest record, and it goes till the crash point. And if any committed transaction is not visible in the databases, we can redo it. And next we have the undo, that is still the oldest record, and if we have partially ones, we can undo them because only committed transactions must be there. So if there are incomplete transactions in the disk, we can undo them. That is mainly what is happening in the Aries algorithm. So this is a very important part. And now, while this analysis is taking place, how we are going to add to this transaction table is, now suppose now I'll explain how we are going to add records from this LSN to the from this log file to the transaction table and the dirty page table. Now this is the transaction table. We have the transaction ID, status and the last SN, and in the dirty page table we have page number and the record LSN. So first here we are starting from the we have to consider the checkpoint first. As I said at the beginning here, we have to start from the most recent checkpoint. So if we take this, first we have, after the checkpoint we are started from LSN 20. So here first transaction 1, we are giving the status as uncommitted initially, and the last LSN number here is, its LSN number is 20. So we give it as LSN 20. And then we are moving to the next record. Next is LSN 30. So while moving to the LSN 30, it says to update, no, I'm sorry, I just couldn't complete this. Now this is LSN 20, update T1 writes P5. So update T1 writes P5 mean we have an active transaction which is T1. So that's what I mentioned here as T1, and status is uncommitted initially. Then the LSN 20 is the last LSN number. So update T1 writes P5. So we have to give the page number here as P5 because it's not old, it's not an already existing data, it's a new record. So because we have assuming that these tables are empty for this before doing this, that is the assumption. So we are as it's updating as this transaction writes to P5, we are giving the page number as P5, and the rec LSN is LSN 20. Very first modified data, that is before, because in P5 this is the first one we are writing here. There are no previous modifications, so that is so what we do is, this is the way we do. Update T1 writes P5, so we give the transaction number here, and as this is uncommitted, we give it as uncommitted, and the last LSN number we give it based on here. Then as it writes to P1, we are entering the record as follows. Then we have the next one, that is update T2 writes P3. So that's a new one, new transaction. So we write the new transaction as T2 and we give uncommitted there. and the LSN last LSN we give it as LSN 30, and here we see update T2 writes to P3. So we are having a new page. So we for the dirty page table we are inserting the new page here, giving the rec LSN as LSN 30. Then it says T2 commit. Now we already have two T2 here, so which is in uncommitted stage. So when it says commit, we remove this off here, and we cut it and we give it commit here. Then after that what happens is T2 ends. T2 ends means this has already this completed transaction is already written to this, so we are no more needing this in this particular table. So what we do is we delete this record. We don't need this record, right? We are not needing this record, so we delete it. Actually we delete this record. So then we have update T3 writes P3. So we are adding T3 is a new transaction, so we are adding T3 record here, which is having LSN 60, and then it says update T3 writes P3. Now already there is a table, already the dirty page table has a record of page P3, and next we have the rec LSN. The rec LSN means only the first modified one. So we are not adding a new record here, because we are getting a new modification here, but record LSN means only the very first data, therefore we are not going to change this. So we are keeping this dirty page table as it is. We are not going to add any record here. So we are going to the next one, that is LSN 70. LSN 70 means the T1 we are aborting. So T1 aborting, so we are cancelling this LSN 20 and we are adding LSN 70 there. So this is because we are aborting. Then this is what we are doing in the analysis phase, and moving on to the redo phase. Redo is starting at LSN 20. That is the smallest rec LSN in the dirty page table. We have to see the dirty page table, and that is the smallest LSN number is 20. So we are starting from LSN 20. So here it says update T1 writes P5. So LSN 20 means page number 5. So page number 5 details are page 5 ones are we redo that, and then we go to the next one, that is LSN 30. That here update T2 writes P3. As there's another record which has P3, we are not going to do any changes here. For this page we are not going to do any changes here. If there are no other records, we have to do the change here. We have to redo the operation here, but as there's another record, we are not going to do any changes here. So moving on to LSN 40 and LSN 50, we are not going to do any changes. Then LSN 60 we have update T3 writes P3. It's right into the P3 page, and as there are no other modifications occurring to P3, we have to redo this operation here. And then we have 70, and that is to abort. And then moving on to the undo phase. Here what happens is, if there are partially done transactions, we have to undo them. So remember, when undoing, we have to add a new record to the log table, that we new CLR record saying we have undone the operation. So undone starts at the highest last LSN in the transaction table. Now here it's LSN 70. So first of all, we add them to the loser set. Loser set means transactions we need to lose during the crash. Now when a crash during the crash, first of all what we do is we check the transaction table, because we have the ongoing during the transactions. During when the crash occurs, we in the transaction table it has all the active records which are there when the crash has occurred. So we can check from the transaction table what are the records which were there when the crash was occurring. So from there we took the last highest LSN number, that is 70. So that's here. So here we first of all we start from LSN 70, but here the ongoing transactions are LSN 70 and LSN 60. So for the loser set, we have the loser set. Loser set means transactions which now when the what are the transactions we need to undo from which set. So those are put to the loser set. From here, that is LSN 70 and 60 because those were the ongoing transactions. Then from here, if we go to LSN 70, it says T1 above. That is transaction 1. Transaction 1 is in LSN 20 as well. So we put LSN 20 to the data, LSN 20 to the loser set, and currently LSN 60 is also in the loser set. Then what we have to do is update T3 writes P3. We have to undo this operation. So what we do is we go and address new CLR record called undo T3 LSN 60. We address CLR record here. Now we from the loser set we did we undone the LSN 60 operation. Now we have to undone the LSN 20 operation only. So to undone the LSN 20 operation, we have to write another CLR record to undo T1 LSN 20. So this is how we are going to undo. We are going backward. Yes, so from 70 we are checking it backward. But still, what we are doing is this log table is increasing because we are adding new records if we are undoing the operation. Now I think I have explained all these things. So now in this question it says modern high performance database system allow buffer frames to be stolen from uncommitted transactions. What problem does this create for the DBMS? So high performance database system allow frames to be stolen. So they are asking about the steal mechanism here. There I said there are frames. Now the disk is stealing the frame from the main memory. So what happens is an uncommitted transaction can go to the disk. So we have to explain that mechanism here. The steal which I already told, so I'm not going to tell it again. And here in the context of DBMS, explain what a database log is. So we keep the database log in order to make sure, because before saying to the end user that we have committed, we make sure that the transaction details we hit to the database log. Otherwise, if there's a crash recovery, we can't. The server can't regain the data. Therefore, that is the purpose of we are having a database log, and the database log entry contains one I showed previously. I already explained the write head logging protocol and what is there in a transaction table and all, and what is happening in the undoing and reading phases. So I'm going to say that again. So this is an MCQ question here. DBMS logs all actions so that it can undo the actions of aborted transaction. Yeah, that is true. That is one of the main functions here. And if you say DBMS are mainly responsible for ensuring transaction consistency, that is wrong, because users are only mainly responsible for ensuring transaction consistency. And a committed transaction is always reflected in the database. No, there are instances, I already explained, that committed transactions may not go to the database because of maybe with high workload. Therefore, a committed transaction, although we say the user that it is committed, it actually is not committed. It can happen. So a committed transaction is not always reflected in the database. So that's all I'm saying about crash recovery. If you all have any questions, you all can ask. Otherwise, we can end the session.
If anyone has questions, you all can put it in the chat so that Isha can answer. If there are no questions, then let's stop the session now. Thank you, Hisha, for